Hello, I'm N Hasan. I'll be presenting the work done in collaboration with my student T. Sweta and my colleague Dr. Priyasha. Effect of gas percentage during minor mergers on the star formation in galaxies. Here's the outline. I'll discuss the abstract, give a brief introduction, describe the numerical simulations we've used Gadget 4 and DICE, simulation parameters, results, and discussions. Mergers and interactions of galaxies are major drivers of star formation. We study the effect of minor mergers on star formation using simulations. We use Gadget 4 code, which has both collisionless and hydrodynamical particles. Our goal is to establish a relation between gas percentage present in the galaxies on the star formation in the merged galaxy. We use 1 is to 10 minor mergers and we run the simulations with different gas percentage varying from 0 to 40 in the primary galaxy. We run 5 isolated galaxies merger simulations where the primary galaxy has 0, 10, 20, 30, and 40% gas in the disk. We observe that the gas particles convert into stars due to the impact of minor mergers. As the gas percentage increases in the primary disk of the galaxy, more number of stars are formed. 37.3%, 45.7%, 53%, 56.8% are the masses of gas converted into star particles in 10, 20, 30, and 40 percentage gas simulations respectively. We also observe that the newly formed star particles settle themselves down in the disk of the primary galaxy. The thickness of disk increases with gas percentage as there are more number of particles newly formed. We also observe that the thickness of the stellar disk contained the older stars also increased due to the impact of the mergers. Major and minor mergers are the main contributors for the changing morphology of galaxies. Major mergers play an important role in transforming a disk-dominated spiral galaxy into spheroids, while minor mergers explain the origin of thick disk and diffuse stellar halo and also contribute to starburst when sufficient gas is present. Minor mergers are more frequent than the major mergers in the universe as they are far more smaller galaxies than the massive ones. The most popular look took to study galaxies, interactions, and evolution is numerical simulations. We use parallel tree SPH code, Gadget 4, created by Walker's Pringles for hydrodynamical simulations. In this code, the gravitation interactions are computed with hierarchical multipole expansion, and gas dynamics is followed by the smooth particle hydrodynamics. We include radiative cooling and star formation in our simulations. For the purpose of simulations, we use distributed and parallel computing facility available at the for Security Theory and Algorithmic Research, International Institute of Information Technology, Hyderabad. The cluster has 28 cores and 56 threads. Each simulation took around 80 CPU hours. We create the initial conditions using DICE code created by Valentine Perret. The dark matter halo is modeled using NFW profile, which is given here. The stellar and gaseous disks are modeled by exponential profile, and the bulge is modeled using the Hernquist profile. The simulation parameters which we have used are as follows. The galaxies with different gas percentages in the primary galaxy are created. The primary and secondary galaxies are in the mass ratio of 1 is to 10. They are placed at a distance of 100 kpc. The simulation is run from redshift of 1 to redshift of 0 present time. The primary galaxies has a viral mass of 100 to the 10 to the power of 10 solar masses, and the secondary galaxy has a virial mass of 10 into 10 to the power of 10 solar masses in all the runs. The primary galaxy contains a dark matter halo, the stellar and or gaseous disk, and a bulge where the secondary galaxy has a dark matter halo and a bulge. The above table lists the different parameters used for modeling primary and secondary galaxies in a 0% gas run. Masses are in the units of 10 to the power of 10 solar masses, and softening length are in the units of kiloparsecs. The table on the left lists the parameters used for the primary galaxy in different runs. The masses of the total disk is constant in all the runs, but the mass of the stellar disk keeps increasing in each run, and accordingly, the number of particles also increase. The results of our work are as follows. Simulations, we ran it with 10% gas, 20% gas, 30%, and 40%. Initial number of particles present is 10 to the power of 5, 2 into 10 to the power of 5, 3 into 10 to the power of 5, and 4 into 10 to the power of 5. And the number of gas particles turned to new stars are 37,308, 91,391, and so on. And the percentage of the gas particles turned to stars are 37.3, 45.7, 53, and 56.8 for the varying gas percentage. The graph shows the number of new particles formed in each simulation with respect to time. As the percentage of gas in the primary disk keeps on increasing, the fraction of particles turning into new stars from the gas particles also increases, and not in a linear fashion. The graph showed the distribution of the old stellar disk particles after the mergers. The particles are similarly distributed all the gas percentage simulations after the mergers, but the disk thickness changes due to the presence of newly formed particles. Here, the graph shows that the distribution of the newly formed particles in the disk, as the gas percentage increases, the particles formed is also more and hence settle down in the thicker disk. As we have increased the percentage of gas in the primary galaxy, the number of new stars forming keeps increasing drastically. In 10 to the power 10% run, 37.3% of gas is converted to stars, 20% gas simulations, 45.7% in 30% gas simulations, and 53% in 40% gas simulations. The newly formed stars distribute themselves into the disk, and as the gas percentage increases, the number of particles increase and also the disk thickness. Thank you.